Hi everyone. Let's start our last lecture on chapters 11 and 12. So in these two chapters, we're going to estimate the performance of a system using a simulation model. And this is the first part of the pre-recorded videos. So as you see on our course map, we are on the last step. So in this lecture, we're going to estimate the system's performance uh, by a simulation model. So we do have a simulation model for a system, and we're going to run the simulation model for a while, and then based on the results, we will estimate the actual system's performance by the simulation data. Okay. As you know, in any simulation model, the input data, the input parameters are generated by the distributions that we have defined for them in our simulation model. So they are generating based on random numbers, right? And anytime that we run the simulation model, we may have a different stream of random numbers. So because of that, the outputs would be different as well. Okay, so in order to make our conclusion about the results and say, so what's the performance of the system by having this simulation model? So we need to use statistical analysis, statistical methods in order to um, have a reliable and trustable conclusion. Okay. Let's say the system's performance that we're going to make our analysis based on that is theta, for example, waiting time. And we have a simulation model and we have the data obtained by the simulation model and we can estimate that performance and we call it as theta hat. So theta hat is an estimation of theta. Okay, so how can we judge about the precision of this estimator? So for example, we can calculate its standard error. So by having the standard error, we do have a measure on the precision of the estimator. And also we can have the width of confidence interval for theta, right? So based on these two, we can say that how precise we are talking about the system's performance, okay? And so the purpose of the statistical analysis that we are going to have in these two chapters is estimating the standard error and also the confidence interval. Okay, and then by using these two, we can figure out how many runs or how many replications do we need in our simulation model in order to have that desired level of standard error and confidence interval. Okay. So in performance analysis, we do have two chapters here, chapter 11 and chapter 12. If we are going to estimate the system's performance, I mean, just for one system, so we are going to estimate the performance measures of a system. That is called absolute performance. But if we are going to compare two or more systems, so we do have variations, we do have alterations for a system, we do have different scenarios, and we want to compare those scenarios, those variations to see which one is better for our system, then we will call this as relative performance, and it's covered in chapter 12. Okay. So in output analysis, let's see what types of simulation do we have. The first one is terminating or transient simulations. So in this type, we assume that the simulation of the system is terminated at some time, let's say TE. So it's not because of our design for terminating the simulation at time TE. It comes from the system, the nature of the system. For example, a bank opens at time, let's say 8:30 a.m. and closes at time 4:30 p.m. So we do have an event in the system which is closing time, and that event will trigger determination of the system or determination of the simulation. I mean, not the system. So for these actually kind of systems, we use the type of terminating or transient simulations. Okay, and we have other systems that run continuously over time, or at least for a very long period of time. So we call these kind of systems as steady state simulations or non-terminating systems. For example, continuous production systems, hospital emergency department, there is no closing time, right? Airport, fire department, police dispatching or patrolling operations, and so on. So as you see here, all those let's say service systems uh, are not, they don't have any closing time, right? They are operating continuously over time. They are discrete event simulations because we do have events over there, and we can model those systems in terms of a DES. But I mean, the system doesn't have any closure time. They are running forever, or let's say at least for a very long period of time. Okay, and these are called non-terminating systems. And here we call the simulation model, I mean the simulation analysis for these kind of systems as steady state simulations. Okay, so in output analysis of a steady state simulation or non-terminating system, again, we need to have a TE because the simulation cannot be run forever. It has to be stopped in some time, right? But this termination time here is defined by the system analyst, okay? By the system analyst. So that's the difference here. I mean, if for terminating systems, the T comes from the system, then from the nature of the system, the banks, the grocery stores, the restaurants, all those kind of systems have an open time and have a closing time, right? But for emergency department hospital, there is no open time and closing time. They are operating continuously over time, right? So yes, for steady state systems, we do have a termination time in our simulation model, but it is defined by the analyst. It's not coming from the actual system, okay? And that's the difference between these two. So when we want to study a steady state simulation, so we are interested in the performance of the system in a very long time, and we increase the the runtime in order to eliminate the impact of the initial status. So yeah, we increase the runtime in order to eliminate the impact of the initial status. Then we can say the result that we obtain at the end, they are not dependent to the initial status. So we can say they are somehow a steady state behavior of the system. Okay. Here we show the performance parameters, performance measures by theta and phi, and our objective here is providing point estimates and also interval estimates for theta and phi. And so the length of the interval estimate will be a measure as the error in the point estimate. Okay, so let's say we do have discrete time data, so we have y1 up to yn. So let's say we have n replications in our simulation and we have obtained these n data. Let's say, for example, the waiting time for n customers, for example, or for n replications. Okay, and our parameter is theta, so we are going to estimate the theta by having these n data. Okay, and or the data could be continuous time data yt over t between 0 to te. Okay, so and it's called continuous time data, and we will have phi here, and we are going to estimate the phi by having these continuous data that we have from the simulation model. Okay, so the examples here for ym for the discrete time data, for example, delay of customer I, the total cost of inventory in week I, for example. So as you see here, these are discrete, okay? Or YT, the queue length at time T, or the number of backlog orders at time T, and it can be varied over time. So because of that, we are saying those are continuous time data, okay? So as you see here, the theta is used for the ordinary mean for discrete time data, and phi will be used for continuous time data, and it will be a time weighted mean, okay? So for our performance parameter, performance measure theta, the point estimation theta hat can be obtained by this. So we know this, it's just an ordinary mean, okay? So theta hat will be unbiased if the expected value of the theta hat equals theta. So in this case, we will call that estimator as an unbiased estimator. But in general, we know that they are not equal, okay? So the confidence interval, in order to have the confidence interval, at first we need to calculate the sample variance. So it will be calculated by this equation. And then by assuming that the output data is normally distributed with mean theta and a variance. So for theta, we are estimating it by theta hat, and for the variance, we are estimating it by s square, okay? So same as before, the confidence interval here will be this: y bar plus minus s over square root of n times t half alpha and n minus 1, okay? And we can also obtain a prediction interval here, which is different than the confidence interval. And it will be this: y bar plus minus s times the square root of 1 plus 1 over n times t half alpha and n minus 1. So as you see here, the prediction interval and confidence interval are different things. So we'll see what are, the concept of the confidence interval and prediction interval, and when and how we can use these two measures, okay? So let's see what's the difference between the confidence interval and a prediction interval. Actually, there are two different things. One is dealing with a measure of error, and the other one is dealing with a measure of risk. So the confidence interval is a measure of error, but the prediction interval is a measure of risk. So let's have an example here, and I will explain the concept of these two in this example, okay? So let's say yi here is the average cycle time of parts production in replication, in a day I, okay? So we know that this average cycle time is distributed normally with the mean of theta and the variance of sigma square, okay? So but they're unknown. So we have a sample data from our simulation, and we can actually estimate the theta by theta hat, right? So the theta hat here is y bar, so it will be a point estimator for the theta, right? But we can't say exactly how far is y bar or theta hat from theta, right? So this estimation has an error, right? And how we can show that what's the error for this point estimation? Yes, for this we do have confidence interval, okay? So by having this y bar plus minus s over square root of n times t half alpha and n minus 1. So by this confidence interval, we will have an interval, and by having the alpha here, let's say alpha is 0.05. So we will say that with 95% of confidence that theta, the actual value of theta, will be in the interval of the confidence interval. Okay, so here actually we are covering our error by a confidence interval and with a confidence level 95% confidence, right? So as you see here, the confidence interval is about the measure of error, right? So now let's say we're going to make a promise about the cycle time on a particular day. So a good guess is theta hat, right? Y bar. But we know that it wouldn't be exactly this, the cycle time on that particular day. Even if we have the theta, I mean the true value of the mean theta, we can say that on a particular day, the cycle time will be theta, because theta is coming from a very long time. It's an average over a very long time, not for a particular day, right? But so when we want to use it, I mean, when we want to have a prediction of the cycle time on a particular day, it will come with a risk. So by a risk, we are promising that the cycle time on that particular day will be this. So that's about the prediction. That's about a risk. Okay. So the prediction interval, which is y bar plus minus s times 1 plus 1 over n t half alpha n minus 1. Okay. So that's y bar. Okay, so now let's say we increase our sample size. We run the simulation model for a very large number of replications. So let's say n, for example, goes to infinity. So in this case, as you see here for the constant interval, if n goes to infinity, then the confidence interval will approach to a point estimation, which is y bar, and it will be exactly theta because n is approaching to infinity. Okay, so yeah, as you see here, by increasing the number of replications, we are reducing the error, and if we have an infinite number of replications, then the error will be 0. But for the prediction interval, if you increase the n, it won't be a point at the end. It will be still an interval. So by having n approaching to infinity, the t distribution will be approached to normal distribution, z half alpha, standard normal distribution, and z half alpha times sigma. Okay, and so as you see here, it will be at the end theta plus minus z half alpha times sigma. So it's not a point. So that's the difference. As you see here, we never can eliminate the risk because it's coming from the nature of the probability, the nature of the uncertainty, and we can't eliminate it. But we can eliminate the error by increasing the number of replications. Okay. So for terminating simulations, we have R replications. So yeah, so we run the simulation for R times independently. So we have R replications and we have the data within each replication and over the replications. Okay, so across each replication, we can calculate these measures. Y bar 1 point, so y bar 1 point or y bar r point will be the average over the data for replication R, for replication 1, for example. And then the variance, sample variance, and H1 or HR. So HI here is the half width of the confidence interval. Okay, so as you remember, the confidence interval was y bar plus minus s over square root of n times t half alpha n minus 1, right? So here we just do have the half of the interval, which is s over n times t half alpha and degree of freedom n minus 1. Okay, and yes, and so in total, in general, I mean, for all the applications, we can calculate y bar point point, which will be the average over all the applications, the standard, the sample variance, and h as the half width of the confidence interval. So here we do have the equations. As you see here, we can calculate these ones. So this is a conclusion on how we can estimate the parameter. How can we obtain a measure of error by having the half width of the confidence interval for terminating simulations. Okay, so we'll have an example in the next part. Okay, thank you.